Hello, and welcome to the second video for section 11.1. In this video, we will introduce more techniques to help compute limits of sequences, and then consider some special types of sequences. We first begin with a tool that helps us compute the limits of sequences that contain some negative terms. Consider the sequence with nth term an equal negative 1 to the n divided by n. The following plot shows the terms of the sequence, which alternate sign from term to term. From the plot, one can guess that the limit as n goes to infinity of negative 1 to the n divided by n equals 0. But how does one show this? Well, with the help of the following theorem. If the limit as n goes to infinity of the absolute value of an equals 0, then the limit as n goes to infinity of an equals 0. So the theorem says that if the limit of the corresponding non-negative sequence obtained by taking absolute values of the terms of our original sequence is 0, then the limit of the original sequence must also be 0. The proof of this theorem is a simple application of the squeeze theorem. Notice that negative the absolute value of an is less than or equal to an, which is less than or equal to the absolute value of an. And by assumption, the limit as n goes to infinity of the absolute value of an equals negative the limit as n goes to infinity of the absolute value of an, which equals 0. Therefore, by the squeeze theorem, the limit as n goes to infinity of an also equals 0. Now we return to our example. We have that an equals negative 1 to the n divided by n, and the absolute value of an equals 1 divided by n. Since the limit as n goes to infinity of 1 over n equals 0, it follows that the limit as n goes to infinity of negative 1 to the n divided by n equals 0. We take a moment to issue a warning. Notice that in the theorem we have the assumption that the limit as n goes to infinity of the absolute value of an equals 0. If this limit is any other real number other than 0, then this version of the theorem is false. The false theorem says if the limit as n goes to infinity of the absolute value of an equals L, where L does not equal 0, then the limit as n goes to infinity of an equals L. For example, consider the sequence an equaled negative 1 to the n. We have that the limit as n goes to infinity of the absolute value of an equals the limit as n goes to infinity of 1, which equals 1. But the limit as n goes to infinity of negative 1 to the n does not exist. We now consider another useful theorem that helps compute limits of sequences. The continuity and convergence theorem says if the limit as n goes to infinity of an equals L, and f is a function continuous at L, then the limit as n goes to infinity of f of an equals f of L. The moral of this theorem is that the images of convergent sequences under continuous functions are convergent. Example 2. Let's find the limit as n goes to infinity of the natural log of n minus the natural log of n plus 1. Note that this limit looks like the indeterminate form infinity minus infinity. To deal with this indeterminate form, we usually perform some algebraic manipulations to make it more manageable. Here, notice that the limit as n goes to infinity of the natural log of n minus the natural log of n plus 1 equals the limit as n goes to infinity of the natural log of n divided by n plus 1. Recall in the previous video we saw that the limit as n goes to infinity of n divided by n plus 1 equals 1. And therefore, by the continuity and convergence theorem, we have that the limit as n goes to infinity of the natural log of n divided by n plus 1 equals the natural log of 1, which equals 0. We conclude this section by discussing two special types of sequences: monotonic sequences and bounded sequences. A sequence an is increasing if an is less than an plus 1 for all n. Similarly, the sequence is decreasing if an is greater than an plus 1 for all n. In either case, the sequence is said to be monotonic. So a sequence is monotonic if the terms of the sequence are either getting strictly larger or strictly smaller with n. A sequence an is bounded above if there is a number m such that an is less than or equal to m for all n. Similarly, the sequence is bounded below if there is a number m such that an is greater than or equal to m for all n. For example, the sequence an equal to n is bounded below by m equal to 0, since all terms an are positive. The sequence an equal to n divided by n plus 1 is bounded above by m equal to 1, since each term an is less than 1. With these two definitions in mind, we have the following natural theorem, the monotonic sequence theorem. It says every bounded monotonic sequence is convergent. We must be careful when applying this theorem. Our setup has to make sense. This theorem more precisely says a bounded above an increasing sequence is convergent, and a bounded below and decreasing sequence is convergent. The following figure shows a bounded above an increasing sequence. Notice how these two properties force the sequence to achieve a limit. Example 3. Show that an equal to n divided by n plus 1 is monotonic and bounded above. We saw earlier that this sequence was bounded above, as for every n, we have that an equal to n divided by n plus 1 is less than 1. The plot of the sequence leads us to believe that it is increasing. But to formally show this, we must show that an is less than an plus 1 for every n. Note that an plus 1 equals n plus 1 divided by n plus 2. So we must show that n divided by n plus 1 is less than n plus 1 divided by n plus 2. We cross-multiply and perform some algebra. N divided by n plus 1 is less than n plus 1 divided by n plus 2, if and only if n times n plus 2 is less than n plus 1 squared. But this is if and only if n squared plus 2n is less than n squared plus 2n plus 1, which happens if and only if 0 is less than 1. Since this algebra led us to a true inequality, 0 is less than 1, it follows that the sequence is in fact increasing and hence monotonic. There is a more fancy method of showing that a sequence is increasing or decreasing using calculus. This method can be more advantageous as it sometimes avoids some tedious algebra. We return to our sequence an equal to n divided by n plus 1. Notice that the terms of the sequence lie on the graph of the differentiable function f of x equal to x divided by x plus 1. Thus, if we show that the corresponding function f of x is increasing for x greater than or equal to 1, then this shows that the original sequence was increasing. Well, how do we show that a function is increasing? We simply compute the derivative and show that the derivative is positive. Using the quotient rule, we compute that f prime of x equals 1 divided by x plus 1 squared, which is most certainly positive for x greater than or equal to 1.